How many of you have ever slid those wooden benches at the back of the gym around from place to place? Okay? Those of you that have, example 1, we're talking about that. So it says, consider the bench below. You know what? Let's pick on Alessio and Owen. Alessio is sliding the bench across the gym floor. And he's sliding it at a constant speed. It's a rough surface, there's friction, and you've pushed on the bench before. You can feel a force pushing against you, so there is some friction, okay? Suddenly, student number 2, Owen, pushes down on the bench. Better yet, we know what Owen would do. You'd be pushing it along. Yeah, you're smiling, you know exactly where I'm going. Owen would come along and sit on the bench, right? Right, okay. So, Alessio's pushing the bench at a constant speed. Owen comes along and sits on the bench. So there's a downwards force F. Technically, it would be Owen's mg, but there's a downwards force F. If Alessio maintains the same constant force as before, what happens to A, the weight, B, the normal force, C, friction, and D, the motion of the bench? It's a good question. Let's put a little A right there. Now, when I say weight, do I mean mass? No, what do I mean by weight? No, now, which force? Okay, so when Owen sits on the bench, does the mass of the bench change? Does the mass of the bench change? No. So does the weight of the bench change? So I'm going to say right now, if we look, here's our before picture, here's our extra push down. I'm making it Owen sitting on the bench, but somebody could be pushing on it. I'm going to argue weight stays the same. Because the mass of the bench does not change, and that's what we're looking on right now. That's what we're looking at right now. What about the normal force? Well, now it's time for us to do a bit of a free body diagram. I drew one here. Now here, it seems to me that if Alessio is pushing with an applied force and we have a constant speed, it seems to me, don't write this down, those two must be the same. Because we're not accelerating, so forces must be, I'm looking forward, that starts with letter B. Balanced. Okay, that's going to be a cue you want to be with. You got to do some homework, okay? So, and if I list the forces before Owen comes along, get the obvious one, mg, and normal force, I think in this situation, the normal force is the same size as mg. Now, let's do our free body diagram. Over here, Owen is pushing down or sitting on the bench. What are the forces acting on the bench? Get the obvious one. So we still have the same mg as before. What happens to the normal force? It has to get bigger, because are we sinking into the ground like quicksand? Are we flying each other like Superman? No, the normal force is going to be larger. In fact, if I was really fussy, the normal force is canceling out mg and that F down. So for B, I think I would say normal force increases. There's my abbrev for normal force increases. Riley, you okay with that argument? And this is one of the reasons why we've said don't go friction equals mu mg. It's friction depends on the normal force, which can change even though the m has not changed. Oh, Riley, friction is what times what? Mu times the... So did the normal force get bigger? Say yes. So what happened to the friction force? Got bigger. Yes? And so now, Alessio, I'm going to argue that our free body diagram would probably look something like that. Vertically, my forces are still balanced. Are my forces balanced horizontally? No. Which way must we accelerate? Now, if we're moving forwards to the right, but accelerating to the left, what does that mean in the real world? I think, Alessio, the bench is going to slow down and come to a quick stop. But we're just looking at immediately after Owen lands on it. I think what I would say for part D is bench slows, and it'll come to a stop. It says, explain your answer using principles of physics. I think we did with our free body diagram and the little argument that we made here. And then usually right around now, I pause and I ask, how many of you have sat on the bench while one of your friends is trying to push it? Yeah, okay. So there's the physics of what was going on there. Now, if they don't want to come to a stop, if Alessio wants to keep pushing, what does he need to do with his initial F applied? He has to increase it, okay? By the way, now think about how you would increase it. You would increase it by actually, with your running shoes, pushing backwards harder on the floor. But that's a whole other issue. We weren't doing the free body diagram on you. We were doing the free body diagram on the bench. I'm going to get technical here because students have asked me this question. How many of you have ever slid something across the floor that was really heavy? Like you really got to put your back into it. Have you noticed that getting it moving is tough, but once you get it moving, you don't have to push as hard to keep it moving? Annika's, okay, we can explain that, Annika. It turns out there's technically two different types of coefficient of friction. There's actually two types of stickiness. There's friction when an object's at rest, and that's usually a little bigger. And there's friction when an object is moving, and that's usually a little smaller. And it's not the normal force that's changing, it's the coefficient of friction that's changing. I'm going to explain this to you because I'm a nerd. But then, Owen, for the remainder of the unit, we're going to pretend there's only one type of mu, and I'm not going to distinguish between the two of them because it's going to get confusing. And this is, again, one of the many areas where I'm teaching you something that's technically wrong because there is no such thing as friction anyways. Okay. The force of friction on an object at rest is called static friction. Because static means not moving or not changing. Example 2, if we pull on a desk with a force of 2 newtons and the desk does not move, then which of the following is true? A, static friction is bigger than 2 newtons. B, static friction is exactly 2 newtons. C, static friction is less than 2 newtons. Or D, there is no static friction. You know what? We're going to vote, but let me demonstrate the situation here. So if I pull on this desk right here with exactly 2 newtons, and I'm pulling with about 2 newtons, and the desk does not move, which of those statements is correct? Okay? Think about what you think is the correct answer. All right, let's vote. Who says, Mr. Duick? Obviously A, static friction is bigger than 2 newtons. It must be. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Annika jumps to the party. 14. Who says B, static friction is exactly 2 newtons? Alessio. Who says C, static friction is less than 2 newtons? Who says friction? What friction? There is no static friction. No one. Either Alessio is going to feel really proud or really silly. And you know what? There's a different level of win for both of those for the rest of us, so it's all good. Convince me. Okay. Ready? Oh, yeah. Oh. Can we, instead of moving, you know what a better word to use would be? A word that starts with letter A, because forces don't tell us anything about movement. They only tell us something about accelerating. So if we pull on it and it's not accelerating, then that means the forces must be, I'm looking for a word that starts with letter B. Which means the correct answer here is? And this is where, Annika, static friction is weird. So you ready? Look up. Static friction is only as big as it needs to be. If I pull with 4 newtons and this table doesn't move, how big is static friction in that direction? Exactly. What if I pull with 4.1? How big, and I am pulling a little harder, how big is static friction just again? 4.1 newtons. What if I pull with 8 newtons? I'm pulling harder. How big is static friction in that direction? Now, suppose the biggest that static friction can be is 10 newtons, and I pull with 10.1. What must happen? Okay? If you're moving something, you can almost feel it through your hands. You can tell, oh, it's just about ready to go. You can tell it's just about ready to crack. Just about ready to go. Totally can. Static friction, that force which prevents you from something moving, is only as big as it needs to be to cancel you out until you go bigger than it can be. Alessio, candy for you for being the only one right. I'm impressed. Is that what you're thinking? Is that your rationale? Or is that a total guess? Yeah. Hey, by the way, which one of Newton's laws did we use, the one that talks about forces being balanced? Which law was that? Sorry? Nope. So you can't write Newton's first and just walk away. Since you couldn't remember which law it was, forces must be balanced since A equals 0. You'll have to actually write out the description. But had you remembered that it was Newton's first, I would have been fine with you writing Newton's first, but since you couldn't, and again, on a test, if I ask you a conceptual question and you can't remember which law it is, just describe it. Those 14 of you that voted A, have I convinced you? Okay. By the way, that would be a bizarre world if static friction was bigger than 2 newtons, because that would almost mean that I could tug on a table, let it go, and it would go slingshotting back over the people in the other direction, because it must be unbalanced, must accelerate. Kind of a strange world. So static friction, I think we're on the next, are we on page 2? Static friction acts when you have 2 objects that are at rest relative to each other. Static friction is what keeps a car parked on a hill, for example. A block of wood will remain stationary on a table until you increase the angle past a certain point. So, do I have a block of wood handy? Meter stick is sort of a block of wood. And if you look back here, is it sliding? No, gravity's pulling it down, but static friction is resisting it. And it'll do it until I go past, oh, there was the magic angle, where now gravity was a lot bigger, able to pull it down the hill. That right there, by the way, is called an inclined plane. That's a 2-dimensional force situation. That's physics 12. We'll revisit all of this, but we're going to ask in physics 12, hey, what if the ground isn't level? What if we're standing on an angle? And if you take physics 12 with me, as soon as I say, what if we're standing on an angle, you'll say to yourself, did he say angle? Components is going to be the trigger phrase that'll jump into your brain right away. That's a preview of coming attractions. So, Annika said she's noticed when she's moving something heavy that the force required to overcome static friction is always a little bigger than the force needed to balance sliding friction. Sliding friction is called kinetic friction. We think, this is why I wrote presumably, because last I checked there was still some discussion as to what exactly was going on at the atomic level. We think that it's because you have to break the welds before objects can move relative to one another. Here's kind of what I think I think something similar at the atomic level is going on. How many of you have ever been in a vehicle on a gravel road with lots of potholes? If you go slow, like 5 kilometers per hour, you feel your tires going in every single pothole. If you speed up a bit, you notice the ride kind of smooths out because you're going fast enough, say, over that pothole that the tire doesn't have a chance to drop all the way down. It catches the far end and there's a bit of a bump, but nowhere near as much as going through every single one. You know what I'm talking about? We think something similar is going on with those microscopic hills and valleys when you're sliding two objects across each other, that as you're sliding them at speed, they don't catch as much. Now, there's a weakness to that analogy, and at the atomic level, the faster you slide something doesn't seem to make much of a difference, where when you drive, the faster you go, the less you feel it, it seems. So that's an analogy, but we think something like that is going on. So if we want it to be completely accurate, typo, we would say something like this. This is me being really nitpicky because there's technically two types of mu, two types of friction. A 5 kilogram object sits on a surface with mu static, mu s, being 0.3, and mu kinetic, mu k, being 0.25. Once you get it sliding, things are a little less sticky. A says determine the force required to move the object. B says the object is pulled with 10 newtons. Find the acceleration and the force of friction. C says the object is pulled with 20 newtons. Find the acceleration and the force of friction. You know what I think this is a good job for? I think this is a job for a free body diagram before we even start. And I got some white space right here, so I think I'm going to put the free body diagram right there. What are the forces acting on the object? Get the obvious one. Is this object sinking to the ground like quicksand? Is it flying here like Superman? So I think we can reasonably say there's a normal force the same size as gravity. Is there friction? Yep. I usually point friction to the left. And then A says, determine the force required to move the object. I think what A is saying is, find F applied, F app, right when it matches and cancels out friction. Got the argument, Kiana? Is that okay? So for A, I'm going to argue that this object will start to accelerate right when F applied equals friction. Technically, when F applied is 0.000001 newtons bigger, but this is the tipping point right there. You okay with that? Okay. From your green sheet, friction is what times what? Pause. Have we started sliding yet? Then it's going to be mu static. F applied is going to be mu s times the normal force. I don't know the normal force. Oh, but look. I know the force the same size as the normal force. Which one? 5 kg is not a force, that's a mass. Don't do that again. Go to your free body diagram, please. Which one? mg, not m, mg. Okay? So I think I can say this. To get this thing moving, it's going to be mu static times mg. It's going to be 0.3 times 5 times 9.8. I can do that in my head. 5 times 9.8 is 49, so it's going to be 0.3 times 49. Well, 0.3 times 50 would be 15. 14.7? Double check me. Yep. How hard do I need to pull to get this thing to start to accelerate? Well, let's say 14.7 is the breaking point. Yeah, okay, fine, 14.70000000001, but there's the breaking point. You okay with that? So how hard do I need to pull? 14.7. Okay, B. Suppose I pull with 10 newtons. Find the acceleration and find the force of friction. What's the answer? Too slow. No calculator. What's the answer? Max, how hard? Oh, Alessio. Because how hard do I need to pull to get this to start to accelerate? How hard am I pulling? Is it going to accelerate? And friction has got to be exactly 10 newtons. Because since it's not accelerating, the forces must be, I'm looking for a word that starts with letter B, balanced. So if I'm pulling with 10, friction is 10. Yeah. Acceleration. I tend to abbreviate. B. No, sorry, C comes after B. Max, how hard are we pulling in C? Will it accelerate now? Okay, so now I'm going to have to do a full equation. Who's winning in C? F applied, the 20. Who's losing? What does winner minus loser always equal? Okay, so if we're starting out generating our own equation, it would look like this. F applied minus friction equals MA. But wait a minute, look up. We're moving. It's going to be kinetic friction. So it wants me to find the force of friction. I'm going to do that right now. In fact, I'm going to draw a little line in the middle of the page, and I'll find the force of friction over here. I got room? Oh, I got room. Friction is what times what? So kinetic friction, moving friction, is going to be mu k times the normal force. I don't know the normal force. Look. I don't know the force the same size as a normal force. So it's going to be mu k mg. How big is kinetic friction? What was mu k? Was it 0.25? Oh, this I should be able to do in my head. It's going to be 49 divided by 4. So it's going to be 10 plus, what's 9 divided by 4? That would be 9 divided by 2, 4 divided by 2 again. 12.25? No? Yeah? 4 sig figs in my head? Okay, just saying. So now if I walk this over to here, because it also wanted me to find the or as we like to think of it, the acceleration, we would go like this, Max, my friend. We would say, okay, how hard are we pulling? Minus, put your calculator down, 12.25 equals, oh, Kiana, how would I get the A by itself? We'll use Kiana's law. Right now, I divide it by 5. 20 take away 12 is 8, take away 0.25 is 7.75, divided by 5. Ooh, what's a good trick for dividing by 5 when it's yucky? Times by 10 and divide by 2. So 7.75 is going to be 77.5. That's still yucky to divide by 2. Maybe I can do that. Be 33.225. No, I missed a decimal. Fine, you can use your calculator. I think I'm off by a power of 10. I think it's wow, totally off. 1.55. I wasn't even close. Boy, must be a Monday. Is it 1.55? Units, it's an acceleration. Direction, they didn't give me any directions in the question, but in the direction of the applied force forward, if they asked for a direction. You're noticing probably most of the time in this unit, I'm asking for the magnitude anyways. I'm not implying a direction. Okay. So, technically, Nicholas, two types of friction, technically. I'm going to pretend there's just one type. You're not going to see in the homework, I think there's one question where I give you a mu s and a mu k. On a test, I'll just give you one coefficient of friction, and you can assume it's the one that you can use for all situations. So, yeah, I thought I had something like that. I wrote here, Prabnur, to keep the math nice, we're going to treat both types of friction as the same thing. So friction equals mu times the normal force, where mu is what we call the coefficient of friction. It's the measure of stickiness or slipperiness. No units. Usually between 0 and 1, but not always. And the normal force equals, oh, do I have an equation for the normal force? You have to find it from a good free body diagram. Now we're going to start to muck around with the normal force, much like a roller coaster would do. Example 4 says, find the maximum force of friction between the mass and the ground for the following objects. This is technically mu static because the biggest force is mu static, but I don't care. A. O and A, what does example 4 want me to find? The maximum what? So I'm going to start out for part A, Owen, by just writing friction equals mu times the normal force. I don't know the normal force, so I'm going to have to do a free body diagram, just a kind of a rough sketch. Although, did they give me a picture? I'm going to label the picture. What are the forces, Owen, acting on this 8 kilogram mass? Get the obvious one. Is this mass sinking into the ground like quicksand? So no. Is it flying through the like Superman? So no. So vertically the forces must be, I'm looking for a word that starts with the letter B. So I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force, Owen. Which one? So I can say here, mu mg. Friction in part A is 0.35 times 8 times 9.8, which is what? $27.44? If I pull with 26 newtons, will this object accelerate? No. If I pull with 27.4, no, but you would probably feel just through your hands, this is ready to move. I can just feel 27.44, now we'll start to accelerate. Okay, cool. Riley, what does this question want me to find? The maximum what? Well, B, the mass is 8 kilograms. Won't it be the same? What did I add in part B that's different from part A? Can you see it in the picture, Riley? Be really obvious. There's an extra arrow there. Just don't even try and categorize it. Pointing which way? This is like the bench and Owen sitting on it or pushing on it, okay? So we're going to start out the same way by saying friction equals mu times the normal force. And we're still going to say, I don't know the normal force. This is a job for a free body diagram. Riley, what are the forces acting on this 8? Get the obvious one. What else? 55 newtons down. See it? Okay. If I push down with 55 newtons, is the normal force going to be bigger, smaller, or the same size as mg? Why? Is this sinking into the ground like quicksand? Is it flying here like Superman? So the normal force is having to cancel out 2 downwards forces. The normal force is going to be bigger. If I really wanted to beat a scale, I would try and make the normal force about as long as both of the downwards arrows, but I just exaggerated. I don't know the normal force. Oh, but look, oh, hang on, no. I can't say, oh, but look. I know another force the same size as a normal force. I'm going to have to figure it out. So are you ready? As soon as you see extra vertical forces in your question, ding, 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 pay attention. Are we sinking into the ground like quicksand, Owen? Can you say out loud? Are we flying here like Superman? That means vertically all the forces must be. I'm going to take it one step further. What that really means is everything down has to equal everything. Yeah. Everything down has to equal everything. Everybody, everything down has to equal everything. That's an equation. What's everything down, Riley? Which 2 arrows are pointing down? 2 arrows. So you ready? Everything down, gravity and 55 has to equal everything up. What? Friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look. I know an equation I can plug in for the normal force. What's the normal force equal to? mg plus 55. I'm going to say that again. What's the normal force equal to? mg plus 55. Wherever I see the normal force, what can I replace it with? No. Wherever I see the normal, okay, ready? Follow me along, George. What does the normal force equal? mg. What does the normal force equal? So when I see the normal force, what can I replace it with? Yes, not mg. Look up. Mu bracket mg plus 55. That's how big friction is, the maximum size friction can be in part B. It's going to be 0.35 bracket 8 times 9.8 plus 55. You could calculate the normal force out ahead of time. I tend to just do it all at once because I'm lazy. So it's going to be, and I got a good calculator, 0.35 bracket 8 times 9.8 plus 55, close bracket. And I get 46.69. Yes? No? Yeah? Yeah? C. I'll have to do that to the side, I guess. Didn't leave any room below. C. They want me to figure out the maximum force of friction. That's going to be mu times the normal force. I don't know the normal force, and I'd better do a good free body diagram here. What are the forces acting on this, Prabnur? Get the obvious one. Good. What else? Can you see the 55 in the question? See it, see it, see it, see it? Which way is it pointing? Here, is the normal force going to be bigger, smaller, or the same size as gravity? Yeah, here, someone is already taking care of 55 newtons of gravity. I don't know what it is, but something is. And so the normal force only needs to cancel out part of gravity. I'll exaggerate it, make it a little tiny arrow so that I know, hey, normal force is canceling out part of gravity. Owen, are we sinking into the ground like quicksand? Are we flying here like Superman? That's because the forces must be, I'm looking for a word that begins with letter B. If I take it one step further, what that really means is everything down has to equal everything. That's an equation. Everything down has to equal everything up. Normal force and 55. I don't know the normal force. I don't quite know it yet here either because I haven't got the normal force by itself. How would I get the normal force by itself? So the normal force is going to be mg minus 55. George, what's the normal force equal to? Wherever I see the normal force, what can I write instead? Mu bracket mg minus 55. It's worth figuring out if your calculator lets you bring back the previous line. Mine does. Second function, enter. Because I've noticed that I can just backspace and change the plus sign to a minus sign, and I don't have to retype everything. And I think of those things. Otherwise, you have to retype the whole schmear. By the way, I should get an answer smaller than not just the 46.69. I should get 27.44, smaller than that even. 8.19. So, to get A accelerating to the right, you would need to pull with more than to get B accelerating to the right, you would need to pull with more than 46.69 newtons. And to get C accelerating to the right, you would need to pull with more than 8.19 newtons. And this is why if you've ever moved something that really heavy across the floor, you lift up as well as push forwards. It's easier to slide it. What if you lifted it all the way off the ground? What would the normal force be as a number exactly? 0. And if you lift it all the way off the ground, what's friction? Because mu times the normal. It still works. It's nice that it works for an obvious answer, but yeah, lift it all the way off, no friction. Why? No normal force. Well, it depends. There's some stuff it's easier to lift. Like if I'm moving this table, for example, it's easier to lift the table because it's not that heavy and the noise is irritating because it makes that heat. Okay, then the table I'll probably lift. If I'm moving a washing machine, probably slide, a little heavier. Example 5 says for each of the blocks below, write a vertical force equation, find the force of friction, write a horizontal force equation, find the acceleration. We're going to do these simultaneously so you can see the difference, because I think the big difference in the diagram is the one on the right, these both have the same mu, 0.12. The one on the right has an extra 15 newtons pushing it down. So you know what? Just kind of draw a line down the middle of your page. Annika, what does A want me to do? There's also a word that starts with letter E, has a Q. Just read me what A says. Write a vertical force equation. Yeah, I can't. You know what I should do first? Free body diagram. Okay? So Annika, let's do the left one together, you and I. What are the forces on the left one? Get the obvious one. Good. Is it sinking into the ground like quicksand? Is it flying here like Superman? So I think the normal force here is the same size as gravity. What name did we give to this 20 Newton, this mystery force coming from off the page? We said we're not going to describe it. We're going to just call it F something. You remember? F applied. Yeah. This is going to be my F applied. Annika, is there friction in this question? Say yes. How do I know? Look up. They gave me a coefficient of friction, so there must be some stickiness there. Which way would friction point? Can you give me a word that starts with the letter L? And I think it's going to be smaller than the 20. If I'm wrong, we'll find out. So I'll draw it shorter. You okay with that? Let's do the right-hand free body diagram. Annika, my joy, what are the forces acting on it? Get the obvious one. What else? I think we would move to the normal force next. Is the normal force here going to be equal to mg? No, there's an extra vertical force. Which way is it extra 15 newtons pushing? So is the normal force going to be bigger, smaller, or the same size as mg? I think the normal forces has to cancel out the mg and the 15 because we're not sinking into the ground like quicksand and we're not flying into the air like Superman. We still have an applied force of 20 and there's still friction pointing which way, Annika? Looking for a word that starts with letter L. I'm not quite sure about all of my arrow lengths, especially this second situation. Maybe friction is so big that we're not moving. We'll find out. But I got my setup. Okay. What did you say A wanted us to find? A vertical force. Okay. We're just going to do A together, you and I, Annika, and then I'll pick on someone else. On the left-hand side, are we sinking into the ground like quicksand? Are we flying here like Superman? What that really means is everything down has to equal everything. That's our equation. What's everything pointing down? What's everything pointing down? Mass is not a force. Read me that. By the way, have you figured out one of my pet peeves? When people call a mass a force. That's not mg, right? What's pointing up? So our vertical force equation on the left is that. Mr. Dewick, if I wrote Fn equals mg, yes. I don't care which side you put the stuff on. Is that okay, Ethan? Okay. B. Are we sinking into the ground like quicksand? Are we flying here like Superman? What that really means is everything down has to equal everything. So what's everything pointing down? Your hint, Annika, is there's two things. There's two arrows. And as a number exactly. Yes. Has to equal everything up. Normal force. Okay. Good. Ethan, what does B want me to find? Friction is what times what? It's on your green sheet. So for both of these, I'm going to write mu Fn. Friction equals mu Fn. Good to see you have an Fn clue. Excellent. Ethan, what's mu? I don't know. What's mu with you? Oh, what does the picture tell me the coefficient of friction in? Okay, so it's going to be 0.12 times the normal force. I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. You okay with that? So if we want to calculate the force of friction, it's going to be 0.12 times 10 times 9.8. I can do that in my head. It's going to be 98 times 0.12. It's going to be 9.8 plus 1.96. It's going to be 10.8. 11.76? Ethan, is that what you got? Yeah, yeah? Okay. B, friction is what times what? Mu times the? Well, won't it be the same answer as on the right? Well, oh, what's the normal force on the right-hand side equal to? So it's going to be mu bracket mg plus 15. Friction is going to be 0.12 bracket 10 times 9.8 plus 50. Do that one in your head, Mr. Well, maybe. It's going to be 98 plus 15. It's going to be 108 plus 5. It's going to be 113. Sure, I can. It's going to be 11.3 plus 2.26, 11.3, 13.3, 13.56? Yeah? 4 sig figs? Just saying. Which answer is bigger, the one on the left or the one on the right? Be obvious. Which answer had a bigger normal force, the one on the left, the one on the right? You know what, Annika? This bigger friction doesn't surprise me because you pointed out we've got a slightly larger normal force. Someone's pushing down on this, making it harder to slide. Owen! Cool. George, what does C want me to do? What I really mean is, who's winning on the left-hand side? Yeah. F applied. Who's losing? What does winner minus loser always equal? There. What about the right-hand side? Who's winning? Horizontal. Who's losing? What's it going to equal? Mr. Duick, how come I got the same equation for both of these? Because it's the same tug of war. The numbers might be different, but I'm pretty sure it's the same tug of war going on between the applied force and friction resisting it. Cool.
Are we sure that?
I don't know. We'll find out if we solve this and we get a negative acceleration. We'll go, uh-oh, go back and check. But it's a pretty easy fix. I've scrolled down. What did D want me to find? There was a D, wasn't there? Oh, find the acceleration. Kiana, how would I get the A by itself in both of these equations? Well, that's kind of cool. So I have this. A equals F applied minus friction divided by M. A equals F applied. That's terribly messy, Mr. Duick. Minus friction divided by M. Cool. What was F applied? 20 minus, oh, I can actually just put in 11.76. Yeah. That's convenient. Divided by 10. You know what, Max? Put your calculator down. What's 20 take away 11? And then take away 0.7 would be 8.3. Take away the 0.06, 8.24 divided by 10. Pretty sure it's 0.824. Double check me, but I'm dividing by 10. I think I can do that without a calculator. Am I right? I hope I am. Yeah. And on the right-hand side, Max, it's going to be 20 minus 13.56 divided by 10. If I was doing this in my head, I would go 20, take away 13 is 7, take away 0.5 is 6.5, and then take away the 6.44 divided by 10. Is it 0.644? Should be, I think. And I got a positive answer. By the way, George, what I had really done, as soon as I got that 13.56 and I knew I was pulling with 20, I knew that the 20 was winning. There was no doubt. Okay. Is it 0.644? So friction is what times what, Ethan? Mu times the? Not mu times mg, because there might be extra vertical forces, but you can figure out how big the normal force is by realizing that everything down has to equal everything. Sometimes if you're lucky, the normal force will be by itself right away. Sometimes you might have to rewrite it to get the normal force by itself a little bit. Meh. Turn the page, or next page over. You don't need to memorize this, but I found, just out of nerdiness, some common coefficients of friction. Wood on wood has a mu of about 0.25. Steel on steel has a mu of about 0.5. But how do we work around that in motors? Oh, we lubricate oil. So that gets it down to about 0.1. Rubber on dry asphalt, anyway, there's a whole bunch of variation. It depends on the temperature. You may have noticed that on a hot, sunny day, pavement is stickier than on a cold winter day. And also your tires are stickier when they're warm. So anywhere from 0.4 to about 0.7-ish. But what I want you to notice is when it rains, you lose traction by about half, which means it's going to take you probably twice as long to stop in a panic stop as you're used to. If you're a good driver, can you change that? No, it's physics. Slow down when it rains. Rubber on ice gets really bad. Steel on ice is about 0.01. So just to give you an idea, these are, oh yeah, good. All values are approximate. They really vary with conditions, degree of smoothness, temperature, etc. Can we have a coefficient of friction greater than 1? Yes, in some situations. Rubber on glass has a mu of about 2. Rubber on glass is really sticky. Doesn't slide well at all. Another area that you might want a coefficient of friction greater than 1 is in a situation where you want a big force of friction, like dragsters. Dragster tire has a mu of about 0.78. Shouldn't a tire with so much friction slow the dragster down? Using principles of physics, explain why a high coefficient of friction is essential for racing. Your hint is draw a free body diagram. You know what? Before I let Alessio call it an answer, let's draw a free body diagram. Here's my dragster. What are the forces acting on it? Get the obvious one. What else? What else? Friction to the left is wrong. What force pushes a car or a bike or your feet forwards? Yeah, friction, my friends, is pointing that way. Your tires push backwards against the pavement. Forces come in pairs. The pavement exerts a friction force forwards on the dragster. So, bigger friction is better. Friction is what times what? So in this equation here, it really ends up being mu mg. Yeah? F equals what? Bigger mass makes it tougher to accelerate. So rather than target the mass, what we say is, hey, let's target our tires. We can make that bigger without increasing mass. Woohoo! Bigger friction. Is that okay? So, increase. That's an abbrev for coefficient of friction. Gives larger FF. And it's friction that makes a car go forward, not the motor, not your engine, not the tires. Friction. Tires push backwards. Now the consequence of, oh, by the way, what else do they do just before a drag race? Right before they start? No. What? How? What? What do they do? No. They do a smoke show. Not to impress the crowd, What's stickier, hot rubber or cold rubber? It's not to impress the crowd. They know that if they heat up the tires, you can bump up the mu. More friction. Now, the crowd likes it, but that's a bonus. It's not dragster tires are crazy expensive too, so you're burning it out faster, but right, if you have sponsors, you're good. How many more am I doing? 1, 2, 3, 4. Okay. I know you're tired. I've been going for about an hour. I'll finish the lesson and then we'll take a break because I want to get this all going. So bear with me. We're slowly increasing our level of difficulty. So example 7, a force of 120 newtons is needed to push a box along a level road at a steady speed. Ding, 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 ding. Ooh, that's something I should really notice. If I'm at a steady speed, what key information does that tell me? And if A is 0, that means the forces must be, I'm looking for where it means letter B. Let's remember that. Okay. If the force of gravity on the box is 250 newtons, oh, they gave me the weight, not the mass. How could I figure out how many kilograms this box is if it has a weight of 250 newtons? Divide by 9.8. I'll do that if I need to. What's the force of friction between the box and the road? And what's the coefficient of kinetic friction between the box? Oh, okay. Suggestions? Well before that, suggestions. I think this is a job for a free body diagram. And I think because I'm doing a free body diagram, I'll just work down. I give you a whole page, yeah? Or half page. So I don't need to divide it in the middle this time. There's the box. What are the forces acting on this box? Get the obvious one. And you know what? I can actually go like this. I can say mg, and apparently it equals exactly 250 newtons. Hey, I'll stick that on there because why not? Is this box sinking into the ground like quicksand? Is it flying here like Superman? Now I'm going to add one more question. Are there any other vertical forces in this question that would change the normal force? No. Here, yes. So I'm now adding one more little check to my mental checklist. So I think we can safely say Fn. And you know what? I can tell you that Fn must be exactly 250 newtons. What that means, George, is wherever I see an Fn, what can I replace it with? Wherever I see an Fn, what number can I replace it with? Okay. What else? Well, there's definitely a force of friction because A says find the force of friction. And this time, it's not what's pushing me forwards. And there must be me applying a force. Oh, did I say applying a force? There must be an F applied. Am I going to draw F applied bigger, smaller, or the same size as friction? George. It is moving. It's not accelerating. Stop saying moving. Max, see what you did a week ago? Stop saying moving. It's steady speed. By the way, this would also work if it was at rest, but it does say it's moving, so I'm being fussy. But steady speed means, okay, cool. Good. All right, now I've got my free body diagram. Awesome. Camille, what does A want me to find? So my first thought would be this. Write this down for a second. Friction equals mu times the normal force. And then, have you ever heard that sound effect of the scratched record bringing things to a stop in commercial? My brain would do that right now because what's mu? In fact, what's B asking me to find? The coefficient of friction. So I would think that, and then I would go, not going to help. Now, I don't know if I would actually write that down next time, but if you're wondering in your notes, we did that because that's my first thought. What Ethan has pointed out, friction equals mu times the normal force. What else is friction equal to? Look at my free body diagram. Did they tell me F applied? In fact, really, I probably should have gone like this. And then I might have even already had the aha moment and said, oh, ha! It's got to be the same size. Okay. Oh, I like this question. I like this question. I like this question. Specifically, I like part B. Camille, what's part B asking me to find? I think, though, next time I won't walk you through part A. I'll feel comfortable just saying, find the coefficient of friction, and I'll expect you to realize I can figure it all out from the free body diagram and filling in the missing gaps. Because now, for part B, Ethan, friction is what times what? Camille, what did you say they're asking me to find? Hey, what's mu? I don't know. What's mu with you? How would I get the mu by itself? Divide by the normal force. Why divide? Because it's multiplying? Yes? So yet another equation, not on your formula sheet, don't memorize it, but apparently one way to calculate stickiness, it's the force of friction divided by the normal force. I don't know the force of friction. Oh, yes, I do. It's the same size as the applied force. 120. I don't know the normal. Oh, yes, I do. It's the same size as mg, which was 250. And this is kind of weird. I didn't even need to bother finding the mass, turns out. I was gonna, if I needed to, divide by 9.8. Didn't need to. It's going to be 12 divided by 25. I think I can do that in my head. Can I, Mr. Dewick? What's the trick for dividing by 25? Timesing by 100 and dividing by 4. So it's going to be 0.3? No, I'm wrong. .48. Wow, way off. That's right, it's times by 4 and divide by 100. 12 times 4 is 48. Units. Can you see it's newtons divided by newtons? Yeah. Units cancel. This, by the way, is actually how you calculate or how you measure mu. You drag something at a steady speed on a surface with a force gauge. You measure the force, the applied force you're having to apply to keep it going at a steady speed, and then you measure its mg. That's how we got these. You gonna make it, Annika? Because you're stretching and yawning a lot. I know, I've been going for a while. I like example 8, I like example 8, I like example 8. Example 8 is a nice question. And I think example 8 showed up in your homework from last day, from friction lesson 1. I'm going from memory, but I think somewhere around question 6 or 7 or 8 was very similar to this. Or maybe I'm thinking about number 9. We'll see. There was a question about stopping distance or something like that, I think. Brebner's checking me out. I can't remember. Okay. Dragster's tires accelerated from rest to a speed of 48 meters per second, a distance of 64 meters. Okay. A says, what's the acceleration? I don't think I'm going to do a free body diagram yet, because I think looking at the information they gave me, I think, Pernell, I'm going to go like this. Try that again. A equals question mark. What does from rest tell me? VI is equal to? Good. What's that, 48? The F. And D is which equation? Can you get the A by itself for me, Annika? A equals squared minus VI squared all over 2D. I agree. So it's going to be 48 squared minus 0 squared all over 2 times 64, which is what?
Get this one in your head, Mr. Dewick.
Well, there's okay, 48 is 4 times 12. Okay, so it's 16 times 3. Oh, okay. No, what'd you get? Is it 18? Shoot, I was going to say, is it 18? And I didn't. I should have. That would have impressed you, even though that would have been a total guess. Almost 2 Gs, not quite. That's a dragster. Yeah, should be some good acceleration. 2 Gs be right around 20, I think 19.6, but close to 20. Okay. Alessio, what does B want me to find? The what force? The what force? You know what? I could go straight to F equals ma. Do I know M? Do I know A? Yeah. So here's my first question. If I gave this to you in the future, I would probably skip part A and go straight to part B and expect you to clue in. I don't know the accelerator. Oh, I can find it. Okay. Anyways, it's going to be 540 times 18. What'd you get, Prabner? 11,000? 9,000? 9720? Anyone else? Yeah? Yeah, okay. C. What is the force of friction between the tires and the road? I think now it's time for a free body diagram. So here's the dragster. What are the forces acting on it, Max? Get the obvious one. What else? The normal force, Fn. Okay, if you say Fn, we'll figure it out. No one, by the way, if you had just said Fn, no one would have noticed that you've forgotten the name. Little hint. And I think there's no other vertical forces, so I think Fn is going to be the same size as mg. What else? Friction pointing which way? To the right. Right? Friction's what makes a car go forward. Is there a force pointing to the left? Well, if the question had said to include air resistance, sure. Although dragsters are pretty aerodynamic for a reason. There's a reason they have that shape, right? There's a reason why we don't make them look like a big parachute or something like that. It's okay. I think this is it. Max, who's winning? Who's losing? It's a trick question. No one. Friction equals ma. Holy smokes, I'm done. Because what did I find in part B? ma. This is kind of weird. My first thought was going to be I was prepared for mu times the normal. Didn't need it, actually. Friction is apparently 9,720 newtons. Has to be. So you can see, by the way, part A, if you're actually part of a pit crew for a dragster, you could actually time this information while you were doing your practice races, and you could then do some nice calculations here. I can tell you what the force of friction between my tires and the road and go from there. I think there's a part D. O and S. Is there a part D? What does D want me to find? Hey, what's mu? I don't know. What's mu with you? What did I find in part C? Yeah, and we are now at a stage in our physics careers where I am going to ask you to find something in order to find something. Or in this case, find something in order to find something in order to find something in order to find something. I would feel okay, I think, giving you this and only asking part D. Okay? Not walking you through part A, B, C to get to D. We're now at that stage. I would consider that a pretty challenging question, but I'd feel okay as a nasty doing that. So I think we're going to use Ethan's friction equals mu times the normal force. Oh, and how would I get the mu by itself? Divide what? Yep. The Fn max. So we get friction over the normal force. Friction, I just figured out, was 9,720. I don't know the normal force. Oh, but look. I know the force the same size as the normal force. Which one? Got to be mg. Did they give me m? Yeah, they did, 540. Okay. So it's going to be 9,720 divided by 540 times 9.8. More than one thing on the bottom of the fraction, so I will have to put the bottom in brackets. $1.83, bigger than 1. Oh yeah, these are dragster tires. I'm expecting a pretty high coefficient of friction. 1.84 if I round off properly, yes? Is it 1.84? Yep. Mu equals 1.84. No units. Okay. You could use this to check the claims of the company that sold you the dragster tires. Well, they said they've got a coefficient of friction of blah, blah, blah. I do, or no, I don't. They're ripping me off. Example 9. Should be, is it one more or two more? Just one more, okay. Example 9 says, find the acceleration of the mass below. Okay. I like this question. What makes this question a bit challenging? Can you see? The extra vertical force. I would have no problem giving you an extra vertical force pointing up or an extra vertical force pointing down. What I'm really saying here is the normal force is not equal to mg. I'm going to have to figure out the normal force. Okay, let's walk through this. What do they want me to find? A. You know what this is a good job for? Did they give me a picture? I'm going to label a picture. What are the forces acting on this mass? Get the obvious one. Okay. What else? Is it sinking into the ground like quicksand? Is it flying through like Superman? So there must be a normal force pointing up. Is it going to be bigger, smaller, or the same size as mg? You know what? Is there an extra vertical force? It's not the same size. So really, it's going to be bigger or smaller than mg. Why smaller? Because someone else is lifting up 25 newtons worth and taking care of that, canceling that part out. So I'll really exaggerate it. Beep. So it catches my eye. What will I call that 45 newtons, that mystery force coming from off the page? We typically call it F applied, so that we don't have to try and make up a story every time. Something's applying a force, I don't care what. Am I done? I think friction is smaller than F applied. How will I know if I'm right? If I get a negative acceleration, then I'll quickly go like this. Yump. And quickly redo my equations. But I think F applied is winning, I think. In fact, I just gave you a hint. Who's winning? F applied. Who's losing? Friction. What's that always going to equal? MA. Kiana, what's this question asking me to find? Can I do this right now, Kiana? Boom, boom, boom. Kiana's rule. I could rewrite that one more time, but... Do I know if applied? Yeah. Do I know friction? Not yet. Okay. So I'm going to write A. Did I give you a whole page?
Yeah.
Yeah. You could probably move down. I'm going to move sideways just so I can keep the diagram on my screen. A equals F applied minus mu times the normal force all over m. Ethan, friction is what times what? Mu times the normal force. Do I know the normal force? Is it mg? No, that's by far the most common mistake kids make. Oh, it's mg. It's not. I'm going to have to figure it out. So I pause. Are we sinking into the ground like quicksand, Owen? Are we flying through like Superman? That means that vertically the forces are, I'm looking for it begins letter B, which means everything up has to equal everything. That's my equation. Everything down, everything up, which is the normal force and 25, except instead of and, that's plus 25, yeah, has to equal everything down. I need to get the normal force by itself. How would I move that plus 25 over? George, can you read this to me? Fn equals what? Fn equals what? So whenever I see an Fn, what can I replace it with? This, in brackets, is going to go right there. I could crunch it right now, but why not just do it once? Because I'm lazy. So, final answer. A is going to be F applied minus mu bracket mg minus 25 all over m. What was F applied? 45? What's mu? I don't know what's mu with you. What's mu? 0.36, fairly sticky. What was m? 5.8 times 9.8 minus 25 divided by, if you have the fancy schmancy fraction button, you still have to include some brackets, but for those of you that don't, it would go like this. Bracket 45 take away 0.36 bracket 5.8 times 9.8. I wouldn't use a bracket inside the brackets. It's too tough to track things, so I use a times sign there. Minus 25. Close off the small bracket. Close off the top. Divided by, do I need brackets around the bottom? Only one thing. I'm jealous of those of you that have the 2-level fraction button because that is kind of handy. But for George and I with our TIs, and we would get positive. So, hey, good. F applied was winning. 5.78? Meters per second squared. So basically, we took friction to another level today. We started solving for mu, and we started solving for weird normal forces. Number one is just asking you to find the normal force. I'll give you a hint. It's either going to be mg plus 15 or mg minus 15, but it's going to be something to do with that 15. Number two, hey, this is just review, finding tension in a rope. It's probably a job for a free body diagram. Number three is so easy that it's tough. Four is good. 5 is good. Ooh, 6, they're giving me a weird normal force because there's an extra vertical force. Ooh, 7, they're giving me a weird normal force because there's an extra vertical force. 8 is good. Ooh, now they want me to find mu. 9 is good. Are you going to just assign all of them, Mr. Dewick? It looks like I am. 10. I can never remember. You might be able to do all your work right on the sheet if you write small-ish. I don't know. Or you can do them on a separate piece of paper. I did include a lot of pictures, and those pictures take up room, so you might be able to write on there. It's up to you. I don't care. It's 10:34. I'm going to give you about 25, 30 minutes, and then we're probably going to start a little bit about the next lesson. What's the next lesson asking? What if there's more than one mass? And the nice thing is, we just have to tweak our winner minus loser equation. I'll even spoil the punchline. Instead of winner minus loser equals MA, it's winner minus loser equals M all times A.